Hello, welcome to the new series on digital circuit design using VHDL. This series is in continuation with the series digital circuit design using ATS. There are two design flows which I have discussed earlier. One was using a schematic entry and using transistors as the preliminary devices, right? And using them I made some digital circuits, and you can do the layout of those circuits and you directly get a ASIC. Now that was a standard cell based design. The another flow is using VHDL. Now VHDL or let's say another hardware description language like Verilog. In this flow we describe a digital circuit using these hardware description languages, and the entire process of mapping these HDL code to the circuit is highly automated. So what we are going to discuss in this series is this VHDL flow, and later on, if the time permits, in the sense of the number of lectures permits, I will go to Verilog flow. But I'm going to start with the VHDL flow. So here we have got the target device, and the target device is uh, is a FPGA, right? So this FPGA which you are seeing, right, this is a entry level FPGA which is a RTX series. It's RTX 7. It's done in 28 nanometer CMOS process, and this FPGA is basically a reconfigurable hardware which sits over here, and this board is known as RTX 7. Now this board is known as Nexus 4, right, and the FPGA is known as RTX 7. Now there are other families of FPGA from Xilinx like Kintek, Vertex, so they are all 7 series. So now there is a basic difference which you should understand. Prior to these 7 series, which are all 28 nanometer CMOS process chips, the earlier ones were Spartan. Now Spartan series had a different kind of architecture, and that is now obsolete. Now 7 series is supported by Vivado, and earlier they used to have a tool called ISE. Now in ISE, up to ISE 14.7, they have a support for Spartan, but then they had a version called Vivado, and from there on they stopped supporting Spartan series. From there on, the 7 series, which is RTX, Kintex and Vertex, that is supported by Vivado. So this Vivado is a tool. It's an integrated development environment which you are which you are going to use. Now in this board, okay, so this board you can find on the Xilinx website. You can find all the details of this board. This is called Nexus 4 board, right? And this is Nexus 4 DDR, right? So there is a memory here which is a DDR memory, and this basically stores all the code to configure the FPGA here. Now what's on this board? On this board there are 16 switches over here, and then these switches can be used as logical input switches, right, to various digital circuits which you design. And then there are 16 LEDs over here just above the switches. There are 16 LEDs, and these 16 LEDs can be configured as output pins for your circuit. So you can have a 16-bit input and 16-bit output. Besides that, there are 5 switches over here, and these can also be used as inputs. And then there are 2 4 7 segment displays over here, right? So they can be used for displaying values here, right? Besides this, there are 3 PMODs here, what you call 3 connectors for PMODs, okay, and 2 over here. So these are for the extension of the board to to various other hardwares, like for example motor drives and stuff like that. Now this board can be programmed using this micro USB type C connector. Directly you can hook it up to your USB port of a computer, and then you can directly write the bit stream to program this FPGA. And next thing what you see over here is this connector. So you can also have the code in the code can be in a micro SD card over here, right? So you can either get the code to program, or bit stream to program the FPGA from here, or you can also have a micro SD card. So whenever you power up this board, the micro SD card is going to uh, to provide the bit stream to configure the FPGA. Besides that, there is a USB support, there is a Ethernet support, there is a VGA output, then there is a audio jack input, which is a mono input, and then there is going to be a microphone over here, right? Most probably it's let me see. Okay, so microphone is on the back side. Okay, there is a microphone here, and then there is a temperature sensor here, there is an accelerometer on this. So there are lots of peripherals inbuilt into this board, and this board is very reasonably priced. Okay, nowadays this is called Nexus, instead of Nexus 4 DDR, it's called Nexus 4 A1 board, right? So they have just renamed this board. Everything is the same. So we are going to use this board for most of our applications now. Okay, so now let's look into what do we have in terms of tool chain. Okay, so to write a code to that FPGA, you need a certain tool chain. Earlier this tool chain was called ISE up to 14.7. This ISE was used for programming Spartans and Vertex in FPGAs. Now these are families actually, Artix, Kintac, Vertex, these are families. I'm going to discuss about them. So I'm going to use Vivado toolchain to write the VHDL code and then synthesize it and then convert it into a bit stream and then write it through the micro USB port onto the board, onto the memory in the board, right? And that's going to program your FPGA, and then we can use those switches to give the inputs and then those LEDs to give the outputs. So that is going to be the goal of this. So I can start directly with here. So I can say file, project, new. So first time it's going to be slightly slow. Okay, so there is a wizard which launches when you say project new, and you say next, give it a name. Okay, so let's say I will call this a Session1, right? And the project location is over here. You can change it. You can create a project subdirectories as the C user Nigam Session1. Next is, it's a RTL project, right? There are other projects which are already, somebody has written a RTL, and then we can do a post synthesis and stuff like that. We'll come to this later on, but we are going to start it as a RTL project. Over here, add sources. So I'm not going to add any sources, but what you have to know here is that the target language is a VHDL and the simulation is mixed, because when you do test benches, mostly test benches are Verilog while the code is written VHDL. Okay, it says add constraints. Now this is also optional. Now what is a constraint? Let me try to explain you this. Okay, I'll explain you. First I'll show you the board. Just one second. Okay, so over here on this board, right, on this board you will see, okay, so this is a miniature window, minimize it. Okay, over here what you see here, these switches, right, these are on off switches, zeros and ones, right? You can give in zeros and ones through this. These switches are hooked up to a certain pin of this FPGA, and these are labeled. So they are labeled over here on the top of the switch, right? Usually the label is like a letter followed by a number. So I'll show you what that is. Then these LEDs which you see, these small ones, below that there are again these pin numbers which are letter followed by a number. So these are mapping directly to the FPGA here, right? And similarly these pins, these are also matching to the FPGAs over here, right? So So what is happening is the following, right? So this is called the IO constraint. So I am basically specifying which physical pin, okay, is connected to which logical pin. So for example, let's say AND gate, right? So AND gate has got, let's say, A and B input, and then Q is the output. So I can use these two switches as A and B input. They have a certain number here that is mapped to the logical input of the AND gate, and then there is a LED here which has again a physical pin number which is mapped to the logical output of that AND gate. So this mapping is referred to as IO constraints. So I am going to do so. Okay, let me verify. So I don't want to help here right now. Okay, so these IO constraints right now you don't need to specify it. You can do it later. Go next. Here is the most important part. Here you are going to target a certain FPGA. Okay, so I have to figure out my FPGA. Okay, so let me pick up a category. So it's a general purpose FPGA. Unlike, you know, automotive and military and other radiation tolerant, this is a general purpose FPGA. Then it belongs to a family called Artix. Okay, so then there are again Artix, Kintex and Vertex, and Spartan 7 is also supported here, you see. So these are all the supported devices. I know my device is Artix 7. Okay, then package type. Okay, so this is a ball grid array with 324 pins. So when you refer to the data sheet of that Nexus 4 board, it will give you a detail of this FPGA, Artix 7 FPGA. And then speed grade is -1. That means it's the slowest one. And then it is all remaining you don't have to worry about. Then the last one which shows up here, right? It has got 324 pins, available IOs, lookup tables, flip-flops, block RAMs 135, right? DSP blocks, right? They are 240, right? And there are no GTP transceivers here. Okay, so this we will come to later on when we do a higher version or a higher family of FPGAs. For now, it is XC, that stands for Xilinx. 7, it stands for 7 series, which is this 7. A stands for Artix. 100 stands for 100 CLB. Now what is CLB? CLB is a configurable logical block. So basically it is a hardware which can be reprogrammed and connected together to make a bigger circuit. So just remember that there is a block called configurable logical block. So there are 100,000 configurable logical blocks, right? And then it has got 324 pins, and speed grade is the slowest one, which is -1. So this is the entry level FPGA. So this you have to do at the start of the project, or later also you can change this. Okay, so say next. Okay, so now it says that, okay, this is the project summary. This is my device here. This is a RTL project, and then there are these things which I haven't specified. They are in yellow. That's okay. I say finish. Okay, so this also is kind of a, this is the ID which I want to give you some details on. Okay, so over here, okay, there is a flow navigator, okay, or a project manager, right? Here you can have the settings which you can look at. Okay, settings here. Okay, so these settings we will discuss once we write a code, right? So if you click it, it'll open up anyways. Okay, so these are some settings which we will discuss when we do simulation and synthesis. Okay, next thing which we want to see is IP catalog. So basically you can integrate a IP into a project, right? Or IP integrator. So basically, let's say you want to use a processor, right? And you don't want to write a VHDL code for a processor because it's very involved. So you can use a ready-made code which is in VHDL or Verilog or whatever, but it is a IP. It is an intellectual property which Xilinx shares with its designers. You can directly drag it as a block, just like in a schematic, and then you can connect the pins, you can create the memory layout and stuff like that, and you can configure your microblaze processor, right? Or for example, you want to use a bus architecture, which is let's say a XC bus, right? Or a AMBA. It's XC is basically a evolved form of an AMBA, or a uh, uh, on chip bus for ARM processor, right? So that IP can be included, right? So like for example, USART, UART, and all that, right? Controllers, you don't have to write a VHDL code. They are available as IPs, and you can build the circuit around those IPs, right? So that's there. Next is simulation. So when you write a circuit in VHDL, you can simulate and see how how it's going to perform, right? Then in RTL analysis, you can also elaborate a design. You can look at what the physical design looks like, how the gates are there and stuff like that. Once you have done the synthesis, you can visualize the synthesized design. Then you run the implementation, and then you generate a bit stream. Okay, and this bit stream is the output which goes to program the FPGA. So we will see one example in this. Okay, and then I will discuss the details. Okay, so this is called project manager. So in this project manager, you can do all the stuff. There are more details over here. I don't want to go into details of each one of them, but as we go used to it, we will know it. So here under sources, you right click here and say add a source, and then you are going to create a design source. It's not a simulation test ban, it's not a constraint, it's a design, right? So you click on add or create a design source, say next. Here you can design a new file, right? So you can say create a file. Now the file type is VHDL, excuse me, the file type is VHDL. You can use a Verilog, you can use system Verilog, right? So but in my case the file type is VHDL, and the location is the location of the project, and say okay. Okay, you have to enter the name of the file, right? So let's say I want to do logic gates. So logic gates is the name of the file. Usually the name of the file should be the same as the name of the entity. Okay, why? Because it's easy to find out which component basically is described in which file. So there is a link that if you name it, you will know that what is inside the file. So that's why I call it logic gates. Say okay. Now here you see there is a default library. This default library is going to be visible to all your projects, but I don't want to do that, right? I want to have a local library here. So I can type here, I can say here my lib. So my lib is the name of the library, and this is local to the project, right? And once it is done, I can say finish. Okay, so once I finish this, I have this IO. So the circuits are going to have input and output pins, right? So let's say if you want to explore all the gates at the same time, right? So they are going to be all the gates which are binary, right? So they will have two inputs, right? So A and B are the inputs. So I can write here. Okay, first of all, I can give a name to the architecture. So entity name is called logic gates. Architecture name is called let's say LG. Okay, so short form of logic gates. Okay, so don't worry about what is entity and what is architecture. I'll explain it. Just give two names to it, and this name can be same as this name, doesn't matter. Then I'm going to say A and B are the two input pins. So they are input pins, and Q is going to be the output pin. So Q is going to be the output pin. Okay, so now over here you see there are three options here: in, out, in, out. So these are directional pins. Okay, and I will explain you programmed IO later on. So just thing to remember is A and B are the input pins, and Q here is the output pin. So that's why it is configured out. This is called the mode, right? This is called the mode, right? And so that's done, and then I can say okay. So once I have done okay, this VHDL file is created with the extension of .vhd. So the name of the file is the same as the name of the entity. Now with the naming conventions you should be clear. The name should start with a alphabet or a underscore, and it can have numbers, so it can be alphanumeric, but the only white space character which is supported is underscore. Other than that you cannot have any white space character, and it cannot start with a number. It has to either start with a underscore or a alphabet. So that's the naming convention here. Okay, so if you double click on this one, okay, so a file will open here which where a lot of code has already been written. Okay, so now the comments usually are going to be 2 dashes. If you put 2 dashes and then it becomes gray, that means that this is just a reminder to you. It's just a comment. It is not so all the comments are single line, you see. Okay, unlike C where you can have multi-line comments, there are no multi-line comments here. So I am going to just put one comment. Okay, so I'm going to say is explore the board. So I'm just writing what this code is going to do. Explore the board. Okay, so I'm going to explore the board. Okay, again there are certain comment lines which I can just delete. Okay, so what do you see here? It says library, so this library is a keyword. Then IEEE library, so the name of the library is IEEE. Then it says use from this library. There is a package here which is called std_logic_1164.all. so up to here this is a package name. Okay, and then .all basically is all the components, all the functions, all the procedures which are here in this package, all the constants, all the data types, they are all available here. And in this package there is a data type called std logic. That's why this library IEEE is included. Now if I was to use bit, okay, so which I'll come to later on, as a data type, then I don't need to define anything over here. Now there are 3 libraries. One is the work library, which is in my case is mylib, right? Mylib is the name of the library. So where do I see that? If I go to libraries, it will list mylib. So this is my library. Okay, so in this library I am creating this component, or what you call a design, right? So if you go back to hierarchy you will see this. Okay, so now another thing is that this is a top level module, because you see there is a green colored box which is basically this file. So this file is a top level module, right? You can also set this over here in settings. If you go in settings for simulation, the top level module is logic gates, and then for synthesis, okay, sorry, elaboration general, okay, here top level module is logic gates. Now this general, when you say logic gates, then this is going to be for synthesis, while for simulation this is the design. So in this case both are the same. Okay, so I'm going to just cancel this. So that's what this triangle means. The green color means that this is a top level design, and then you can have a hierarchical design below it. Okay, so now this library, okay, is the local library which is local to my project, mylib. Then there are 2 more libraries. One is basically standard and other is IEEE. Standard is implicitly visible to any code you write. So you do not have to write this library standard then use standard.standard.all. You don't have to do that because it is implicitly visible. But IEEE library is not implicitly visible, so it has to be explicitly specified here. So the library is called IEEE, and then the package is called std_logic_1164, and then everything in that package is going to be included. It's called .all. Like in C, you have a hash include. Similarly, you have a inclusion of this package over here. After that, you see entity. So everything which is blue is a keyword. So entity is a keyword. Then the name of the entity is, then there is a port description. A and B are input ports in, and std logic is the type, q is the output port, std logic is the type, and then and the entity name. Then architecture lg of this entity is, and here I'm going to specify the functionality. So entity is basically outline of the circuit, which usually specifies the ports or the pins which through which you are going to talk to the circuit, right? While architecture is what is the functionality of that circuit. So that you are going to define here. So for example, I can say, okay, I can have, instead of q, I can add more. Okay, so I can put here q and comma, so I can do q or comma, then I can do q NAND comma, then I can do q NOR comma, then I can do q not. So underscore is allowed, right? Q not comma, and then I can do q XOR comma, and then q XNOR, right? And that's it. Now, okay, so somewhere there is an underscore over here. Okay, fine. So now these are my output pins, each one. So for each gate, right? AND, OR, NAND, NOR, NOT, XOR, XNOR. So these are output gates, right? Now I can write here a equation. Okay, so this is called a statement. Okay, so I can say q AND is assigned. Okay, q AND is assigned what? AND between a and b. So this is as simple as that. So this is known as a conditional statement or a data flow statement. This is a very basic statement which is a data flow statement. What it says is that signal is going to flow from input A and B to the output Q underscore AND. Okay, and then instead of equal to, I'm using this less than equal to or assigned. So whatever is the result of A and B is assigned to Q underscore AND. So similarly I can write here Q or is assigned A or B, right? And then, so is there a double underscore? Okay, then I can say Q NAND is assigned A NAND with B, and then Q NOR is assigned A NOR with B, and then Q NOT is assigned A NOT. So it is only one input gate, right? So I can say not A, right? And then you can say Q XOR is assigned A XOR B, then I can say Q XNOR is assigned A XNOR with B. Okay, so these are all the gates. Okay, and there is no red line which says that this code is perfectly fine, right? So this is the code which I have written. Now I have to test this code, right? So to test this code I would have to do a synthesis or simulation, sorry. So what I have to do is I have to do a simulation. So I can here say run simulation. Okay, so I don't have to set up the test bench. It will do it on the fly. Okay, meanwhile this does that, I will go to So look at this. Okay, so this is a window, okay, where I have the inputs and output signals specified here. Okay, at present they are all undefined, that's why you see a U here. Okay, so I am going to just say, just clear all this stuff. I'm going to reset this. Now I'm going to set A and B values, right? And so A and B values, and then the corresponding output values can be computed. I am going to simulate for, let's say, 100 nanosecond. Sorry. Okay, 100 nanosecond. So basically I'm going to upgrade every 100 nanosecond. So here I'm going to specify the value, right? Force constant. So I'm going to force a constant here, or rather I can force a clock also, right? So for now I'll force a constant. Okay, so let's say I force a 0 here. Okay, and this one also I right click it and force a constant which is 0, right? So now if I was to say run for this time step, it is going to give me the outputs. So if I say run, so what do I see? I see AND is 0, OR is 0, NAND is 1, NOR is also 1, right? NOT is 1, XOR is 0 because they are the same bits, XNOR is 1. Okay, so now I can do one more thing. I can start changing it. So I can force this constant to be 1 this time. Okay, so once you do this and you run it for another 100, so what do I see? See, AND is 0, OR is 1, NAND is 1, NOR is 0. So that makes sense. NOT is 0 because A NOT, right? Then XOR is 1 because they are unequal bits, and XNOR is 0. So that's done. Then I can force this to be 0 and force this to be 1, right? So this is all what we were doing in ADS in the other series, right? So I will do this again. So now again you have seen the change. AND is 0, OR is 1, NAND is 1, okay, NOR is 0, NOT is 1 because A is 0. Then XOR is 1, XNOR is 0, and the last one is 1 1. Force a constant 1 1. Okay, and then I hit again. So here AND is 1, NAND is 0, OR is 1, NOR is 0, NOT is 0, XOR is 0 because they are equal bits, parity is even, right? XNOR is 1 because it's a even parity. Now you can also do a view all to see all these states, right? So this is how you simulate the design, right? So once this simulation is done, okay, I want to look at what it looks like in a schematic. So if you go to schematic, say okay, okay, so now you can clearly see what it is. Okay, Q NAND was using a AND followed by inverter, and then AND from here. Similarly, OR was NOR, OR followed by inverter is NOR, and then there is a OR, and then you have got A and B. So NOT is basically NOT of A, and then what you see here is a XOR gate, right? So XOR gate of A and B is here, and XNOR gate. Okay, so there is no bubble here. So this is a XNOR gate. So this is a RTL view or a schematic view or a gate level view, right? Okay, so this is your code and that's your schematic it has created. Now once you have done that, you can run the synthesis, but okay, I'm not going to carry on from here. I will introduce something to do with VHDL before I carry on with this. Okay, so now here I'm going to put this aside. So you know what this software is. You are going to write a code, and that's going to translate into the gates, and then you will be able to synthesize it and implement the real gates in the, they will be not the gates, they will be lookup tables. I'll show you later on. So for now I'm going to stop this over here. Okay, what I'm going to explain you from the in the next session is how do you write the VHDL code and some of the syntax of VHDL, and I'll also try to explain the difference between VHDL and Verilog. So for this session is just an introductory session what we are going to do, and the introduction was to the hardware and to the integrated development environment called Vivado. So these two we are going to use for exploring the digital circuit design, right? So for here I'm going to stop here.